Welcome Dr. Jonti Horner to here at the UNSW, and he's agreed to give us a public talk for the UNSW Physics Outreach Unit happening on April 25th. So Jonti, can you tell us about your presentation that you'll be giving for us?
So I'll be talking in this presentation about the work I've been doing for the last few years since I moved here to Australia back in 2010. And essentially what I'm talking about is testing planetary systems to destruction, crash testing planets. So as you'll see in the little demonstrations that we do, the way we find planets around other stars is actually, with a very small number of exceptions, indirectly. What I mean by that is that rather than seeing the planets themselves, we're seeing their effect on something else. We're watching a star do something that's unexpected and inferring from that unexpected behaviour that there must be planets.
So you don't directly see the planet, you're looking at the movement of the host star.
There are a small number of planets for which we have got direct images, but that's less than 1% of the total sample we know. In fact, it's about 0.5%. Because in order to be able to directly image planets, we need kind of a perfect storm of everything to be set up correctly for us to have a chance of doing it at the minute. By analogy, it's a bit like standing on the one side of Sydney Harbour, looking at night across at the lighthouse on the other side, looking at the lighthouse beam, and trying with the unaided eye from several kilometres away to see moths flickering around the lighthouse. You just can't do it. You need to be very, very fortunate. You need really bright moths in order for you to be able to see them separate to the star. So what we do instead is we watch how stars behave over time and look for them doing something unexpected, something periodic, that might be an indication that there's a planet there. Now, being scientists, we can't just say, well, this star's doing something strange, there must be planets. We've got to instead try and strengthen that argument by ruling out all the other possibilities. And a lot of work goes on into proving that, for example, it isn't star spots on the star like the sunspots we see on the sun that are giving this periodic behaviour, that it is truly something that can only be explained by planets. But from that indirect behaviour that we're observing, from the wobbling of the star, from the blinking of the star, we infer the mass of the planet, we infer how the planet moves around the star. But we then want to test that the planets that we think are there actually make sense. So at this point, it's only a hypothesis. We're saying, here is this behaviour that we can't explain unless there are planets there. So we need to then be able to test those planets and see whether they really make sense. And that's where I come in. So I'm mainly a theoretician. I use a computer program that's like a solar system in a box. You put in the planets that you think are there, you let them run forward in time, and you see how they interact with each other. They pull on one another with their gravitational pulls as they move around the star. Now, most of the stars around which we're finding planets are at least 1,000 million years old. Some are like our sun, 5,000 million years old. Some may even be 8,000 or 9,000 million years old. And our current understanding is that planets form at the same time their stars do. They form in synchrony with the star forming. It's an inherent part of the star formation process is that you also get planets. So those planets must have been there for as long as the star's been there. So let's say we're looking at a young star that's only 1,000 million years old. Stars have very long lives. And we find what we think are two planets moving around it. Those two planets must have been moving around that star for the last 1,000 million years since they formed. They can't have formed more recently because there would have been no material there for them to form from. What I do is take those two planets and put it into my model, into my solar system in a box that uses the laws of gravity that were explicitly detailed by Isaac Newton 300, 400 years ago and have been, I wouldn't say they've been changed since then, but how you implement them has been refined. Uses a very clever way of handling the laws of gravity that allows us to work out how two planets pull on one another, how they change one another's orbits as they go around a star. Now, in order for those planets to be believable, they have to survive for a long time. The likelihood of us finding two planets in the final 10 years of a lifetime of 1,000 million years is vanishingly small. We're seeing the last 10 years of 1,000 million years of evolution at this second. That's unlikely. It's not to say it can't ever happen, but it's very unlikely. So what I do is I run many, many copies of the planetary system we think is there, typically 100,000 or so. And I look at how the planets interact with one another for a period of 100 million years. I'd love to do more, but we're limited by computer time. These runs typically take about 100,000 to 1 million hours of computer time to run. Very intensive. And what I'm testing is to see how the systems interact with one another. We don't know exactly the paths the planets are following. We only have a small number of observations, so we have a little bit of uncertainty. So I look at how the planets interact with one another on these timescales. In some cases, we find systems that simply don't work. And I'll talk about these in the talk and what they're telling us. But the essential take-home message is that not every star that wobbles, not every star that blinks, has planets causing that wobble or causing that blink. Or maybe there's more to the system than we currently know. And that's indicated when we look at a system and find that all of those 100,000 trials, 120,000 trials, whatever, crash, fall apart within 1,000 years. Something's wrong. The hypothesis doesn't work, the story doesn't work, we need to go back and get more data. At the other extreme, there are systems we find where even if we ran 1 million trials, nothing would happen. They're so stable that the planets definitely work. But beyond that, they're so stable there's probably room in there for you to throw more planets into the mix and for it still to work. So that's an indication that we could find more there. It's worth continuing to look. The final situation is possibly the most interesting for me. That's where across the different trials you do, you find some that are very stable and some that are very unstable. Because that's the point where our understanding of the interaction of the planets, our understanding of how they pull and push on one another, how they change each other's orbits, allows us to tighten our understanding of their parameters, of the orbits that they're on, and allows us to better understand, to better characterise these planets that we are essentially confirming are there. So it's a really good example of one of the ways we do science, in that observers see something unexplained, theorists come up with a story to explain it, and use that story to make predictions. That's a really important part of the scientific process. A theory, in the sense of how we talk about theories in science, has to make predictions, it has to make testable predictions, because that's the way that you attempt to disprove the theory. You can never essentially prove a theory. If I have a theory that I flip a coin and it will always fall heads or tails, I could test that 1 million times, get 1 million times head or tails, but that hasn't proved the theory. All I've done is failed to disprove it, because on the 1,000,001st flip, the coin might land and balance on its edge. And that one observation would be enough to throw the theory away and start again. Now, 1 million trials down the line, you're fairly confident that the theory holds water, but the one observation is enough to throw it away. And so the important thing with the theory, as we view them as scientists, is not how good an explanation it is of what we already know, but how well it can predict what we observe in the future, how well we can test it. And that's the really important part, and that's where I can come in, because I'm testing the hypothesis, I'm testing the theory that the cause of these unexplained wobbles, winks and blips are actually planets going around these stars.
Yeah, but it's interesting that you're actually saying about what science is. I think because the public sometimes gets confused about how we actually conduct science. And
that's where it's very easy to manipulate. So there's a lot of controversy about climate change, which is probably something people are wary of discussing. There's a lot of problems about vaccinations at the moment, or alternative medicine, or windmills, wind farms. And there are a lot of cases where the disconnect between how scientists think about and talk about science and how most people who aren't scientists have been taught at school to think about it. We use a different language, but we don't realise we're using a different language.
You're talking about sort of cross-disciplines between different sciences. So you've got a biologist, a physicist, an astrophysicist, a climatologist, and each one of those have their own different language. Can you care to comment on that?
So it's a common problem, because we all think in the terms that we're used to when we hear what people are saying and interpret based on our own experience, everything like this. Language is actually incredibly contextual. I read a fascinating study on a website called The Conversation, I think it was a few weeks ago, talking about how you can remove letters from a sentence, and you can actually remove a huge amount of the information from that sentence, and people will still be able to read it and understand it, even if every second letter is missing. We're incredibly good at picking out nuance, at hearing what people are saying, even if the volume's low and we're breaking up, things like that. But we hear that in the context of our own experience and our own education. So there's a common difficulty that scientists in one field have talking to scientists in another, in that some of the terms they use are understood in different ways when they're talking to each other. And this is exactly the same as when scientists communicate with non-scientists. There's a big disconnect there, because the scientific terms and the scientific education you get at high school are different to those you get on discipline-specific courses at university, and everybody's language diverges. And it's one of the great challenges for scientists to communicate any idea that is controversial, whether it's a scientific idea that is doubted or a non-scientific idea that's pushed forward. It's quite hard to debate when you're talking with this contextual gap. But it's also something that we as scientists have to deal with when we do multidisciplinary work.
Such as astrobiology.
Exactly. Astrobiology is awesome, fascinating and exciting. And it's particularly good because it brings together people from all walks of science.
So this question may be a bit controversial in the sense that as a scientist, what is your stance on finding extraterrestrial intelligence, or indeed if they do exist?
There are two possibilities, essentially. You either imagine that life is so incredibly, vanishingly, unbelievably improbable that in a universe which has more galaxies in the universe than there are stars in our galaxy, where there are more stars in our galaxy than there are grains of sand on every beach on the planet. Around each of those stars, around most of the stars, there are planets, so there are more planets in our galaxy alone than there are grains of sand in our planet. If you can imagine that life is so incredibly improbable that it would never happen and we're a statistical fluke, then we're alone in the universe. If you even imagine that life is infinitesimally more likely than that, still vanishingly improbable, with more planets in the universe than there are grains of sand on the Earth, grains of sand in the solar system, we have to say that life must be out there somewhere.
So statistically,
unless it's so unlikely.
Yeah.
The question then is, how nearby will that life be? How easy will it be to find? And that ties into the question of how easily life gets going. And this is something that people are studying at the Centre for Astrobiology here, looking out in the Pilbara in Australia at the oldest evidence for life on our planet. The question of how quickly life became established on Earth, because that ties into how easily life gets started. The more easily life gets started, the more widespread it is in the universe, and the closer to us the nearest planet with some form of life on will be. So as you gradually make life more and more probable, then the next nearest intelligent civilization, if there are any, will be nearer and nearer to the Earth. The next nearest inhabited planet, even with microbacteria, things like that, will be nearer and nearer to the Earth. Now, I think, in all honesty, if I had to hedge my bets, and this is pure guesswork, but it's a personal opinion, I think we're more likely to find life in our solar system before we find life beyond our solar system. Now, it's been fairly well established that bacteria can survive transport between planets. There's a guy in the UK who's done fabulous work firing frozen bacteria out of guns at 5 and 10 kilometres a second and proving that when they hit a target, the bacteria can survive. They're incredibly durable. There have been experiments done on the space station that have shown bacteria can survive in the vacuum of space in a dormant state for months, if not years. There are bacteria that can live in the heart of nuclear reactors. Streptococcus radiodurans, I think is the name of the bacteria, that lives at radiation levels that will kill anything else and sterilise it. Life is incredibly durable. There have also been a lot of studies showing that when we get an asteroid or a comet impacting on the Earth, that can eject rocks from the Earth entirely without vaporising them. It can eject lumps of solid rock to float around the solar system. Some of those rocks will land on Mars, some of those rocks will land on Europa or on Venus or wherever. If they're carrying with them viable bacteria, and we know that bacteria are so durable, so versatile, then it's likely that even if life only began on Earth, that life has been seeded through the solar system over the eons since. Now, whether any of it took a foothold is another question, but I think in the next decade or two, we'll learn the answer to that question. And there are a number of locations in the solar system where we think that life is certainly feasible.
Yeah.
Doesn't mean it's there. Mars is a good option.
Yeah.
Mars, we think, back in the early days of the solar system, was warmer and wetter than it is today. But even in recent times, there may well occasionally be liquid water under the crust, under high pressure. There may be occasions, even in the recent past, where liquid water has flown on Mars. And we know from the dry valleys in Antarctica, the most Mars-like, the most barren place on our planet, that bacteria can survive in permafrost. So there could be life there. We have other locations in the outer solar system that are far more different to the Earth, where there may be liquid water. There are 2 or 3 of the moons of Jupiter, Europa, Ganymede and Callisto, may have subsurface oceans. We're fairly confident they do. Those oceans aren't kept warm and kept fluid by light from the sun. These moons are too far away, but rather they're heated and continually kept melted by volcanic activity, which is driven by the squashing and squeezing of those moons by the planet Jupiter, tidal effects. The same things that cause the tides to rise and fall at the ocean on Earth, magnified many hundreds of times, because Jupiter's the biggest, baddest bully in the solar system.
So the solar system is teeming with life. Why aren't we actually, well, could be teeming with life, I've seen. There's so many different locations where we could find life. Why aren't we sending stuff out there, or why can't we see the life out there? I guess as a person from the public, why all this potential?
If there was life there like us, walking around broadcasting radio, we'd have found them. The problem is that compared to the Earth, these places aren't as nice places for life to thrive. Or in the case of Europa and Ganymede and Callisto, whilst they may be very good places for life to thrive, atop the ocean sits a 10 kilometre, 15 kilometre thick layer of solid ice.
Yep.
Trying to see through a layer of solid ice 15 kilometres thick that's 1 billion kilometres away is still challenging even with the technology we've got.
Surely we've got space probes and
we do
stuff.
have space probes, but we've never landed on any of these moons around Jupiter. It's very challenging, very costly to get out there. And landing on the Earth is fairly easy. We've got an atmosphere that can slow you down. Landing on Mars, as we saw with the incredible 7 Minutes of Hell video.
This is Curiosity.
With Curiosity, yeah. Mars has less atmosphere, less braking available, so you've got to be more inventive and more clever to land there, but Mars still has an appreciable atmosphere. Europa, Ganymede, Callisto, the moons of Jupiter, the big moons of Jupiter, have no atmosphere. So you're coming in to land on them at speeds of kilometres per second with nothing to slow you down.
It's a big engineering challenge.
It's a big engineering challenge just to land there. Then you've got a 15-kilometre ocean to get through kilometre ice sheet, to get through before you even get to the ocean. Where's the life going to be in the ocean if it's there? Well, it's unlikely to be at the bottom of the ice sheet because all of the heat, all of the energy, all of the nutrients are at the bottom of the ocean where the volcanoes are spewing material into the ocean 100 kilometres further down. It's beyond us now. It's not going to be beyond us for very long. So the evidence is really hard to find, but that's the whole cool thing about science. Science isn't about the questions we've already answered. It's about the questions that still are there to be answered. That's the challenge. It's why we come into work every day. If we knew everything, the universe would be a very boring place. And the really cool thing
there'd be no need for science then.
Exactly. But we're at a situation now where it's realistically, within my lifetime, we could find life beyond the Earth. We could answer that question that's been bugging people for ever since.
Are we alone? Yes.
Are we alone?
Yeah.
And that would be a very interesting discovery. It'd be very interesting to see how society handled that at large, how people cope with the idea that life is not unique to the Earth. So one of the problems we have with talking about life in the universe is that we cannot have a sample of one. We know of one inhabited planet where life has taken one particular course. You need to think about how quickly life got going. So that life has been around on Earth for possibly 3,800 million years. The earliest evidence for life is somewhere between 3.2 and 3.8 billion years ago, and it's still heavily debated. For most of that time, that life would probably not have been detectable, certainly from beyond our solar system. It's only maybe 500 million years ago that life started to become sufficiently complex, really started to modify its environment. Now, I'm not a geologist, I don't know the exact timeline, but life has been a procession of increasing complexity punctuated by extinctions. And that kind of catastrophe curve ramping up like this, who's to say that couldn't have started a bit earlier or taken longer? Also, all of the stars you see in the night sky are different ages to us, and their planets have been around for different amounts of time, but they're made of different compositions. The bulk is still going to be hydrogen and helium, but the amount of the things that make us Earth, the amount of carbon, nitrogen, oxygen, varies tremendously across our galaxy, across the universe, because all of that material is made in the furnaces inside stars. So every time a star dies and flings material back into space, it enriches the universe with the elements that go on to create life. So you can imagine that the universe is possibly becoming a more and more welcoming location for the development of life as time goes on, because there are more of the building blocks available. But that's maybe a double-edged sword. If you get too much of them, you change the composition of the planets, you change the way the planets are built. One of my colleagues here, Dr. Jade Carter-Bond, does loads of really interesting simulations of looking at how planets form when the chemistry is a bit different. And it turns out that you can change the chemistry by a small amount, and you end up drastically changing the way a planet looks and feels. So if we expect life to be exactly like us on a planet exactly like the Earth, that really narrows things down. What we'll probably do in the search for life in the early steps, when we start looking at the planets we're finding now to search for life there, is to look for life like us in a location like the Earth. Now that's sometimes misinterpreted as being narrow-minded, like we're looking for what we already know, we're not being imaginative, we're not saying life could be anywhere, let's look everywhere. But it's rather a practical consideration. If we had unlimited time, unlimited money, unlimited telescopes, we could look at everywhere at once and just look for the unexpected. But initially the observations to go from we know of a planet to we know of life, and these are still a long way away, will be punishing, they'll be very time consuming, they'll be very expensive, which means we'll only be able to look at 1 or 2 planets at once at the very start. As time goes on, technology gets better. As we push that boundary of technology back, we'll be able to look at more and more. But if you can only look at 1 or 2 planets, you need to think about which offers you the best prospects for finding life. And that means you've got to be informed by what we already know. We know that there is life on Earth. So we know that one type of planet that definitely can host life is a planet like the Earth. So for those first explorations, it makes most sense to look for what we already know to maximise the chance of success. Even if further down the line, we can look for the unexpected, we can look for life in places that we didn't expect. And that's the lesson we take on from solar system astronomy, is that the more we look at our solar system, which is the planetary system we know in the most detail, the more we find locations where life could exist, where life could thrive. So in a location that we never expected, suddenly we have yet another place where, whilst it probably isn't there, life could exist.
So life could be teeming throughout the whole solar system. We don't even know.
It could. I mean, we've got a planet here that's probably, every time we have an impact like the one that killed the dinosaurs, flinging bacteria into space, seeding the universe. You know, it could easily be that in 10,000 million years' time, when the Earth is a long distant memory, having been swallowed by the sun, there is life on another planet that was seeded by a rock flung out from Earth. It sounds like science fiction. It's certainly unlikely, but it's not beyond the laws of probability. If you think how many bits of rock with bacteria will have been blasted off the Earth over the last 4,000 million years, who's to say that one of them won't eventually land somewhere where it can take root? Just like trees that drop their seeds in the ocean, most of those seeds never find land, but all you need is one to land on a beach and lay down roots, and suddenly you have a new island with plant life on. It's the same kind of thing. It's a theory called Pamspermia. It's still controversial because it's such a long shot. But just because something's a long shot doesn't mean we can rule it out. Again, it doesn't mean that it's the case. You know, it may well be that life is only on the Earth within our solar system, that nothing ever took root. But certainly the opportunity has been there in the past. And some people even suggest that, turning the idea on its head, life on Earth may not have originated on Earth, but might have originated on Mars or Venus. And the Earth was seeded with that life.
Could have been seeded from another solar system.
Could even have been seeded from another solar system. Now, these hypotheses are only bordering on the line of being a theory. They're very hard to test. They don't really make predictions. So they're more speculation than theories, and that's again back to how we view science. But the really, really interesting test of this is if we do find life on Mars. Now again, that's a long shot, no guarantees on it. If we find life on Mars and we can study that life, we can look at its genetic makeup. We can see whether it has the same basis as us, whether it has DNA with 4 base pairs with the same setup as us. If the life on Mars is different to life on Earth, that's an awesome result. That's really exciting because that's telling us that life on 2 planets that are next to each other got started totally separately, has a different origin, because it's totally different to any life on Earth. That's a really exciting result. On the other hand, if we find life on Mars and we find it has the same chemical composition as Earth, the same genetic background, the same 4 base pairs, the same DNA, then that's a really exciting result as well, because that's showing us that life can be transported and remain viable and seed from planet to planet. Doesn't answer the question of whether life began on Earth or whether life began on Mars or whether it began elsewhere, but it's telling us that life is more durable, more transportable, more pervasive than we thought. So if we discover life on Mars, which we may never do, then either way, it's an absolutely groundbreaking, earth-shattering, incredible result.